In this video, we're going to do some review of logarithms. The expression log base 2 of 8 means the exponent that goes on 2 to make 8. Well, 2 cubed is equal to 8, so the exponent we're looking for is 3. In other words, log base 2 of 8 is equal to 3. Something like log base 3 of 1/3 means the exponent that goes on 3 to make the number 1/3, so that would be -1. And the exponent that goes on 7 to make 1, so log base 7 of 1 is equal to 0. Now there are two bases that are particularly important to us. When we write ln x, so ln x, that is just a fast way of saying log base e of x. E is the number that's about 2.718. It's got infinitely many decimal places there. So this number e will be particularly important when we work with exponential functions a little bit later on in the course. So whenever we see ln x, we're going to think log base e of x. And the other base that's particularly important, if we write log x with no base indicated, that is automatically base 10. So log x means exactly the same thing as log base 10 of x. And for that reason, it's going to be particularly important that we remember to write the base, because if there's no base indicated, then it's automatically base 10. So let's try a little bit of quick practice with these two particularly important bases. If we write ln e, remember that means log base e of e. So the exponent that goes on e to make the number e, that would be 1. Ln, let's say ln 1/e means log base e of 1/e. In other words, it's the exponent that goes on e to make the number 1/e. That would be -1. Log of 10, because there's no base indicated here, this automatically means log base 10 of 10. In other words, it's the exponent that goes on 10 to make the number 10. That would be 1. And log of 1000, because there's no base indicated here, it's automatically base 10. So we're asking for the exponent that goes on 10 to make 1000. That would be 3. Next, let's look at the change of base formula when we're working with logarithms. Often we'll want to do something like calculate log base a of b. And to do this, we'll often have to use our change of base formula. So the change of base formula tells us that we can always use the function ln to do this calculation. Log base a of b is equal to ln of b divided by ln of a for any values a and b for which this logarithm is defined. So you're always doing ln of your number divided by ln of your base. Well, let's try a little calculation. Let's say we wanted to calculate log base 2 of 17. In other words, we're trying to figure out what exponent goes on 2 to make the number 17. Well, if we look at our calculator does not have a log base 2 button. So this is where the change of base formula comes in handy. Log base 2 of 17 is the same thing as ln of 17 divided by ln of 2. And we can do this calculation on our calculator. So we can grab our calculator and check, comes out to about 4.09. And if we wanted to double check this value, we could always head back to our calculator and just check that if we take the number 2, raise it to the power 4.09, yeah, we do get something around 17. It's not going to be exact because we've approximated this value here to begin with. For part B, let's do a little bit more practice with our change of base formula. This is something that will come in handy when we're looking at derivatives of logarithmic functions. We're going to simplify the expression log base b of e. So according to our change of base formula, anytime we have log base something of something, we can rephrase that entirely in terms of values of ln. So we could rewrite this as ln of our number, ln of e, divided by ln of our base. Now, if we think back to ln of e, remember ln is just a short form for the function log base e. So what exponent do we need to raise e to make e? That would be 1. So the fact that ln of e is equal to 1, this is a fact that we will use repeatedly throughout our calculus course when we're looking at derivatives of logarithmic and exponential functions. All right, so really, to get this fully simplified, we've got the expression 1 over ln of b. Next topic that we can look at is log rules. We've got 3 rules that allow us to simplify logarithms. First of all, if we're taking the logarithm to any base of a product, we can simplify this as log base b of our first factor plus log base b of our second factor. So the logarithm of a product turns into a sum of logs. And we'll see that when we're doing calculus, this actually comes in really handy when we're calculating derivatives. Notice that the base b does not change here. So the base b has to be carried all the way through this expression. If we're taking the logarithm to any base of a quotient, so one function divided by another, this turns into a difference of logs. In other words, we get log base b of the numerator minus log base b of the denominator. Third and final log rule tells us how to handle something like log to any base of a quantity that's raised to a power. And this is also another function that comes in really handy in calculus, makes the process of taking derivatives much easier. This power here can actually come right out in front of the log. So this is the same thing as n times log base b of x. So this one here is known as the power rule for logarithms. So to get the hang of these rules, let's just try one quick example here where we simplify an expression involving a log. So let's say we take log base e, so ln of a big expression here. Our expression looks like x times x plus 1 all cubed over, let's say, x plus 4 all squared. So we're going to see if we can use our log rules here to simplify this expression. Well, first thing we might notice inside this logarithm is that we've got a quotient. We've got one function divided by another function. So using our second log rule, we can say this is ln of the numerator. And I'm going to keep brackets around that so it's clear that ln applies to that entire numerator. And then we're going to subtract off ln of the denominator. Notice that the base of our logarithm does not change as we're doing this. We originally had a ln, so a log base e. We're going to have lns all throughout this expression. Now, looking at our first term here, we've got a product now inside the logarithm. So we can break that up into a sum of logarithms. This is the same thing as ln x plus ln of x plus 1 cubed, and we've still got minus ln of x plus 4 all squared. So final bit of simplification that we can do here is using our power rule. First term is as simplified as it's going to get, but for the second term we can grab that power there. Because this entire quantity inside the ln is raised to a power, that 3 can come out in front and we can make it plus 3 times ln of x plus 1. Similarly, if we look inside the third term here, inside the ln, the entire expression is raised to a power, so that power there can come out in front and we'll have minus 2 times ln of x plus 4. So we'll see when we're taking derivatives that if we try to take a derivative of a function like this, it can be quite a long calculation just because there would be a quotient rule involved and some other rules, possibly a product rule involved. Whereas if we actually simplify our function first, we'll see that taking the derivative of the expression is really not too bad.